Here's another problem on gravitational forces. Now here I'm given three masses A, B, and C, and the value of each mass is given in the diagram as well as the distances between their centers. And it's also given that the mass B, that's the one in the middle, the 0.1 kilogram one, is initially at rest. And I have to calculate its speed when it moves 0.4 meters to the right. Now, to solve this problem, you can use energy conservation principles because we have an isolated system. That is a system where there are no external forces at play. The only forces involved here are the gravitational forces exerted by the masses on each other. So there are no external forces, and hence you have an isolated system. Now, the thing with an isolated system is that if you take the total kinetic energy, that is the kinetic energy of all the particles or objects in the system, and add to it the total potential energy, that is the energy due to the interactions of the objects with each other, then this sum is going to be equal to the total mechanical energy of the system, which is a constant in the case of an isolated system. Now, because this is a constant, that means due to some internal change in the system, due to some internal change, like in this case, the change that we're talking about, is the motion of the mass B 0.4 meters to the right. So because of such a change, there will be no change in the total mechanical energy. It's a constant, and so the right-hand side of the equation is 0, and we have the change in kinetic energy plus the change in gravitational potential energy equal to 0. Now, this is a very useful equation to solve the problem because I'm concerned with the speed of the mass B, right? So that's where the kinetic energy comes in handy. So once it moves from its initial position to some place 0.40 meters to the right of the initial position, then initially its speed was 0, it was at rest, and I'm interested in figuring out the final velocity v. So the change in kinetic energy is going to be 1/2 of m, and m was 0.10 times v squared, where v is the unknown, and the initial kinetic energy was 0. So now all that's left is to figure out the change in its gravitational potential energy. Now let's talk about its placement in the gravitational fields of the masses A and C. Now, gravitational potential energy is energy due to the position of a mass in some gravitational field. So initially, when it was at its initial position, it was 0.4 meters away from the 5 kilogram mass and 0.6 meters away from the 10 kilogram mass. So let's calculate this initial potential energy that I'm going to call U1. So that is going to be equal to negative sign. U1 equals the, first of all, I'm going to count in the field due to the 5 kilogram mass. So that's negative g times 5 times 0.1 divided by the distance between their centers, which is 0.4. And of course, the object B is in the gravitational field of both the 5 kilogram mass and the 10 kilogram mass. So I'm going to add another term for the gravitational potential energy due to its presence or its position in the 10 kilogram mass's gravitational field. So the distance there was 0.6. Yes, exactly. So I can actually factor out this negative g times 0.1, and I'm left with 5 by 0.4 plus 10 by 0.6, which according to my calculator is, well, I'm going to get a negative 2.92 g calculation, and I'm going to deal with the value of g later. So next up, we have the gravitational potential energy at its new position, that is when it moved 0.4 meters to the right. And once again, let me look at my diagram. So it moved 0.4 meters to the right. That means it's the distance between the centers of B and C is 0.6 minus 0.4, which is 0.2 meters, and the distance between the centers of A and C is 0.6 plus 0.4, which is 0.8 meters. So let me just plug in this new information for the new potential energy. So that is going to give me negative G times 5 times 0.1 divided by 0.8 plus negative G times 10 times 0.1 divided by 0.2. And once again, just factoring out this G and 0.1, I'm going to get 5 by 0.8 plus 10 by 0.2, which according to my calculator is, what is it? Speak, calculator, speak, and it's, oops, I plugged in the wrong values. 10 divided by 0.2 and 5 divided by 0.8. So that is, that's going to give me a negative 5.63 G. So that's the gravitational potential energy at its new position. Now that I have both potential energies, I can calculate the change in the object's gravitational potential energy, and that is U2 minus U1, which gives me negative 2.71 times G. That's the number of joules of potential energy that has decreased. So coming back to the equation that we were about to use, that our solution centered on. So the change in kinetic energy was just half times m, which is 0.1, times the unknown velocity squared, plus this change in gravitational potential energy. And I might as well just shift it to the other side to get a plus sign, and I may finally just multiply this by the value of the constant, and that is going to give me a very small number, which is negative 1. Oh, sorry about that, positive, because I just transferred it to the next side. That is 1.81 times 10 to the negative 10, and I'm just gonna multiply by 2 and divide by 0.1 as well to finally get the answer. And of course they take the square root all in 1. So multiplying by 2 and dividing by 0.1, that is going to give me, after the square root, that is 6.01 times 10 to the, that's negative 5 meters per second. So that is the velocity of the mass B when it moved, by the time it moved 0.4 meters to the right. As you can see, gravitational forces don't do a very good job when it comes to accelerating masses, especially if the masses exerting the force aren't of a planetary or astronomical scale. So anyway, be sure to like and subscribe, and thank you. See you next time.